We're going to go ahead and get started. So, some quick announcements really fast. If you still want to be a member, we're definitely still taking membership. Talk to JT during the meeting for Rainbows. Afterwards, Rainbows, could you raise your hand? This is Rainbows. So membership is $30 for the whole year. It's like 10 a quarter. Helps pay for pizza. There's lots of good reasons for membership, so you should do it. Also, coming up here, we have Frag Night, which is on the 16th of November. So that's not this Friday, but next Friday. Location to be announced. Almost always we have Frag Night here. We're looking at the possibility of moving it to the BSC, but we haven't worked out the logistics of that yet, so we'll keep you posted. If you don't hear anything further on the location, it's in here. Also, not only did I caps, but I bolded the free pizza because I know what you guys really care about. So, quick show of hands, who would be interested in a hacking workshop? Okay. Without saying too much, there's the possibility that we'll be having one of those sometime this quarter or early next quarter. So I'll keep you guys posted. I just wanted to gauge interest, so it looks like we have enough to make it run. So that's exciting. This week, for our speaker, we have Ryan Schapowski, and he's going to be introducing himself. There we go.
Okay. So hi. My name is Ryan Schapowski. I'm a professor in the math department here. I just got hired last fall, so this is only my second year here, my fourth quarter. So you might not have seen me around campus too much. I would love to see you guys in some of the classes I teach. I mostly do applied math stuff. I'll tell you a bit more about that in just a second here. And I'm going to be talking about a brief introduction to GPU computing. And a quick outline of the talk is going to be, I'll spend just a minute or two just telling you a little bit more about me, my background in computing and that sort of stuff, because I'm coming from the math department, so that might seem a little surprising that I do a lot of computing, in fact. And then I'll try to go into GPU computing. Why GPUs? Why do we use them? What are they powerful for? That sort of stuff. What's the general model for GPU computing? So this is sort of the ideas of what we call GPU computing, or GP squared U computing, whatever, lots of crummy acronyms. But that is basically what are the assumptions that go into building a program or a code that's going to use your GPU, and why are those assumptions there? I'll talk specifically about OpenCL in this talk. I'll mention the main competitor to OpenCL in a sense. It's a competitor, but also sort of orthogonal. And then I'll actually go through a full example of using OpenCL to do something really trivial, just so that you see how the model, or how the implementation ends up working on such a simple example. Okay? The assumption here, not necessarily all of you are programmers. I don't know, show of hands, how many of you are programmers? Like good C? Okay, I guess the hacking thing should have sort of indicated that you will be capable of doing a fair amount of programming. But anyways, so there's going to be a lot of code thrown at you just in general in that example, so that the interested people will see what it is. Okay, let me go on with who am I. I don't have slides for this. I was just going to go off the cuff. So Ryan Schapowski, that's my name. I'm originally from Winnipeg, Canada, so central Canada, North Dakota. I was born and raised in that area at least. I moved around a lot when I was younger, settled back in Winnipeg for grade 5 and on, basically. I did my undergraduate at the University of Manitoba, which is also in the city of Winnipeg, where my undergraduate was originally going to be math and physics. I realized physics is boring. Then it was going to be math and computer science because I wanted to get a job. And then it just so happened that math and computer science, actually, they were offering all the classes at the same time, and I picked computer science. So my undergrad degree is actually in computer science. During that degree, I started doing a little bit of research with someone in CS on graph theory. That got me interested, realizing that there's something called research out there, and so I decided to go on to graduate school. I went to the University of Illinois at Urbana-Champaign for 2 years in the computer science department, where I did work on computational or scientific computing. They have a group in the CS department there that does scientific computing, which is design and implementation of highly parallel algorithms for solving basic, or not basic, but various applied math type problems. They have in particular a group that does rocket design, and so they have amazing models of what happens inside a rocket as it's taking off, all the combustion that's happening there. They do this computationally, they figure it out. They actually did some modeling on this whole this piece of styrofoam stuff that happened with, what was it, the Challenger, I guess? Is that what it was? Anyways, there was a big group of people doing computational science there, as well as NCSA, one of the main supercomputing groups, is at UIUC. And so that really got me interested in this sort of stuff. After 2 years, I headed to the University of UC San Diego for a PhD, and that was when I made the transition from CS to math. Because I realized that not everybody does computational stuff in the computer science department. Some computer science departments, turns out, they do computational stuff, but they have no care about what the math is behind it. They just care about the code. And that wasn't interesting to me. I wanted to do more of the math as well. So I moved into math, and I spent 6 years doing a degree there, a PhD in mathematics. My degree was on approximating solutions of a particular type of differential equation. And then I spent another 3 years there and then moved up here. The 3 years there was as a postdoc, and then I moved up here as faculty. So that's who I am. My background is fairly computer science heavy. So much so, let's go even way further back. When I was in grade 3, I was, how old are you then, like 8 or 9, whatever. My parents bought a Commodore 64, a computer with 64 kilobytes of memory. And this thing was amazing to me. This is a computer, you would turn it on. At the top of the screen, it would be a blue screen with like gray text on it. At the top it would say, welcome to Commodore 64, tell you a little bit about how much memory the computer has, whatever. And then give you a blinking cursor. And what could you do with that blinking cursor? You could start typing basic programs. And what I mean is the computer programming language BASIC, you could immediately start typing programs there. 10, space, print, hello, enter, 20, space, go to, space 10, enter, and then it spews out hello infinitely many times, or at least until you turn it off. And so I taught myself to program at a really young age, and that's just come with me this whole time. Okay, so my computing background, it's there, but I actually do care a lot about the math behind what I do as well. Today, not going to talk about math pretty much at all, other than that the example is technically a mathematical computation. So let's get down to computing. We understand that we can write a program to do some approximation, we can solve some equation, whatever it is. We can figure out an algorithm to do that sort of stuff. Why are we going to do it on a GPU? So what are GPUs good at? That's what we need to figure out. So what are GPUs good for? Not the best, let me turn down the lights maybe something. Anyways, whatever. The picture is it here somewhere? Yeah, Skyrim. So computers are really good at doing computer graphics. We understand that. Really good at talking about people who take heroes to the knee. What else are they good for? Well, they're also good for really crappy graphics. Minecraft. They're good at really gory graphics. Gears of War. I guess this is technically maybe on an Xbox or something, still really underneath the hood computer. My favorite, Borderlands, cell shading. I love this stuff. I think it's amazing graphics. This is what they're good for. They're really good at doing graphics. That's what we understand. That's what they're designed to do. And as gamers, we want them to be better, to push more pixels to the screen faster so that our frame rates are higher, and that sort of stuff. So what are they really good at doing though? What is a GPU really actually doing underneath the hood? Why is it so good at doing that graphics? Well, what they're really doing is they're doing many, many, many independent calculations for every frame. A single frame takes a couple thousand calculations, a couple million calculations probably these days. And what are those calculations? So they are what we're going to call the kernel in this context. They're just some fast thing that you want to do to a stream of data. Okay? In terms of graphics, we'll sort of come back to this analogy, but those streams are the vertices of some mesh that's describing a surface in your 3D scene, for example. So that's how all this stuff is done. And then at the coordinates of your mesh, you've got coordinates in some texture, and you need to be able to map that stuff and figure out what it should look like on your screen. And the kernel is what's called these vertex shaders, or fragment shaders. And that's what they're really good at doing, is these hugely parallel computations on streams of data where one vertex gets handled completely independent from another. Okay, what else are GPUs really good at? Well, they're really good at, in my case, so I play games, I really do, but in my case, what I really care about in this context is the fact that you deep-pocketed gamers out there going to Frag Night on Friday, you guys spent a lot of money to make these GPU manufacturers keep pushing the boundaries, keep making a faster and faster GPU. So I get to take all that money that you guys have spent and use it for something that I care even more about than playing games. Maybe that's actually a lie. I care a lot about playing games. but care about aside from playing games, and that is to actually do computing. So solving some sort of equation, doing something like that. I get to do it even faster because I can use your investment, basically. Just to show you that this is not a lie, that your money has really bought me a better computing platform. Here's a shamelessly stolen diagram from a talk I found online. So I think this is interesting. I stole it from a talk that was by two people I've never met, Wen-Mei Hu and John Stone, and they credited the figure to John Owen. So I don't know if they stole it or if he knew about it either. But anyways, this is now the third step away. This is a graphic that only actually goes up to the middle of 2008, showing the gigaflop. So that is the number of floating point operations on a gigascale. So what's that? 10 to the 9, 10 to the 8? I forget. Whatever. 1024 times something. Whatever. On some scale, between a CPU made by Intel, so the blue line at the bottom, versus the two main graphics manufacturers, AMD or what used to be ATI, and NVIDIA, and what they're pushing on their graphics cards. So the number of floating point operations that a graphics card was capable of in the middle of 2008 was already, what's that, like 5, 6 times, 10 times what a CPU was capable of doing. And that's just the computations. The memory bandwidth is similarly affected. I don't have a graph for that, but the actual bandwidth between the processor and the memory is also increasingly disparate between the CPU and the GPU. And this is obviously something that Intel would love to not see as the case, but there's a reason why these GPUs are capable of such high gigaflops, okay? And it's because they're stupid. The kinds of flops that they can do are really simple. A CPU is designed for general purpose computing. It has a memory access model that's really complicated. Every piece of memory can be written in red, all this sort of stuff. Whereas GPUs, they get them fast by restricting what you can do on them. Okay? That's how they're so fast. So long as you are going to be able to write code that takes advantage of what a GPU was designed to do, you'll be able to take advantage of these flops. Okay? That's what it sort of comes down to. This is why GPUs. Any questions about why GPUs? Or do we understand the main benefit? So long as we can program to what they're capable of, we can get a lot more power, a lot more computing power out of them. Okay, so what about the general model? What is a GPU good at? As I said before, they're based on an idea called stream processing. Okay? So what is stream processing? Stream processing is basically the idea that you have something called a stream, and it's just somehow a set of data that comes. Think about it in a line, it actually doesn't matter. The idea is that you have a set of data that you will perform some kernel of processing on. So we'll call the kind of thing that you're doing to your stream a kernel. And the goal is that the hope is that all of these different computations can be done independent of each other. If there's dependencies, if there's an actual serial nature that you have to compute this before you compute this, before you compute this, you're not going to be able to take advantage of your GPU. But if you can think about your thing as compute all these things at once, and then get me the answer and do something with it, that's when a GPU is going to be beneficial. This is a model of parallelism that's called data parallelism. Somehow you think about your data all as being acted on in parallel, also known as loop level parallelism. The idea being that somehow, maybe under the hood you have a for loop, for I goes from 1 up to 10 billion, do something. If every iteration of that for loop is independent of each other iteration, do them all at once. That's what we're talking about here. That's what GPUs are good at. We call the stream, we call the data the stream. We call the thing that we're actually doing the computing on the kernel. So in the context of games or graphics applications, the streams are our vertices or fragments of a scene, and the kernels are the vertex and fragment shaders that are then going to make our textures look nice and pretty and get mapped to the screen. We're not going to talk about that side of things. We care about kernels that are computational in nature. I want to use them to do something more specific. As I was saying though, how they get things to be fast is they put restrictions on stuff. So one of the biggest restrictions is that inside your kernel, your data is split up hierarchically, first of all. And I'll get to the memory model in a second, but inside a kernel, you have to pass data to it, and then it's going to pass data back. There's no data that's allowed to be both. There's nothing you can pass to the kernel. It's allowed to then act on it and change it and pass that back. It has to be either input or output. Everything inside your kernel has to be thought of as that way. Everything that's at least passed into your kernel. There can be local memory there as well, we'll talk about. And so the ideal GPU application is something that has tons and tons of data, and that each of those pieces of data requires something significant to be done to it, although the example I'll show you later is literally add two numbers, that's it. So it doesn't have to be that significant. And that it has to be as independent as possible. So, because every time there's some sort of a synchronization point that's necessary, that's going to limit how much you can get out of your GPU. Okay? Anytime that there's something that has to happen in serial, you're going to lose out on speed up. So OpenCL. I guess on this slide, this is when I'll mention that there are two main competitors for, I say competitors, but they're not really, two main choices for how you can go about doing your GPU computing right now. There are others out there, but the two main ones are choosing OpenCL or choosing CUDA. You might have heard of CUDA as well. I forget what CUDA stands for. The U is unified, that's all I remember. D, probably device. But anyways, whatever. CUDA is, the reason why these are sort of competitors and sort of not, is that CUDA is NVIDIA's proprietary way to write GPU computing code. And so it only works on NVIDIA cards, and more specifically only fairly recent ones. Well, fairly recent in computer, not in computer terms, I guess maybe 5 or 6 years old even. So that's not too recent in computer terms. Whereas OpenCL is owned by the Khronos Group. I say owned, I don't know, actually the trademark I believe is owned by Apple. Khronos Group is in charge of publishing the specification for OpenCL. I believe Apple has the last say on the specification though again. And what's important about it is OpenCL is designed in the same kind of way as OpenGL was, which was by a group of designers who all wanted to make an interoperable way to deal with something. OpenGL being your graphics applications, push pixels to the screen. OpenCL being, okay, now use those graphics cards for computing. Okay? So OpenCL is an open standard that you can program to and then try to use your same code on an NVIDIA graphics card, an ATI or AMD graphics card. It's even such an open standard that really it makes sense to think about it even just in multi-threaded applications. So if your processor, my processor has 4 cores and then twice as many if I allow with hyperthreading turned on, so it pretends like it has 8 cores, I can essentially use OpenCL to try to use all those cores simultaneously, even on a processor. So the programming language or the standard, the specification, doesn't care what underneath the hood is doing your computing. It just tries to give you an interface to act with it. Okay? That's why I like OpenCL. I like open things a lot better than I like NVIDIA's closed proprietary choice. However, CUDA has actually been around a little bit longer. It is fairly mature because of that. They just released the 5th specification. And a lot of people do use CUDA. So feel free to pick whatever you want. But so what is the OpenCL model? The OpenCL model is based on the following. So this is a picture that I've taken from a talk by the Khronos Group. The Khronos Group is, again, the one who's in charge of the specification for OpenCL. They also do OpenGL, like I said, and a number of other standards. And this is a talk that's just available on their website that tries to give you an introduction to OpenCL. And what is it? Basically, the idea is that you have a single host. You think about your host as your program running on your CPU. Okay? There's something doing something there. Your normal application is your host. You then have access to multiple compute devices. This might be multiple graphics cards in the same computer. My home desktop, I've got 2 GeForce GTX 570s sitting side by side in SLI mode. That's what my compute units are. Okay? Each compute unit is then logically broken up into each compute device is then logically broken up into compute units. That's actually, it's logical or not, it doesn't really matter how you think about it, but there is this notion of compute units. On a GeForce 5700, or not 5700, 570, a GeForce GTX 570, it has 480 what are called CUDA cores, CUDA coming from the term for NVIDIA's proprietary thing, and that is, those are your individual compute units. These are actually, my processor is a 4-core processor, well, my graphics card is a 480-core processor. But again, those are stupid cores. They can do simple computations really fast, but they can't do what my processor does, and that's why they can minimize it, that's why they can miniaturize it so well. Then within a compute unit, you have logical divisions of processing elements, and then this is where we'll talk about that. Well, actually, we won't really talk about this setup much more than this, but we'll see where OpenCL goes with all this in a minute. So this is the basic structure. You have a host program, he has access to these compute devices, and he's going to farm off work to those compute devices. That's essentially what's going to happen. Okay, now in words. There we go. OpenCL is a single host program, which is usually your standard C or maybe C++. There's Python bindings for OpenCL, whatever you prefer. You have a single host program. The computation to be parallelized. So the idea is that there's something that you want to be done on a huge vector of data, let's say, or maybe an array of data, or 3D array of data, or whatever, some structure. And the idea is that you break it up into what are called work items. A single work item should be somehow an atomic, really small computation, okay? And it should be capable of being done in parallel with all of the other work items. If you can't do that, then you shouldn't be doing GPU computing because you're not going to get the speed up that you want, okay? The code for a single work item is called a kernel. So you're going to actually write not only a host program, you're also going to write a kernel program, okay? And it's in a C-like language that you'll see later. So you actually write another program and you give it an extension .cl, and this is going to somehow be your actual compute kernel itself, okay? And then for platform independence, the really neat thing about this, if you ask me, is that you write this .cl file that contains your kernel, and it's actually at runtime. So while your host is running, it reads that file in, this source file, this .cl file, reads it in, farms off makes a function called the OpenCL's libraries, which will then go and compile that at runtime. So there's some runtime compilation of your kernel. That has to be the case for this to be device independent, for it to work on an AMD card and on an NVIDIA card, because those two things underneath the hood have completely different chips that don't understand the same instruction sets, that sort of stuff. So for device independence, it has to be this way. I actually think this is a benefit otherwise, and some of the stuff that I hope to use GPU computing for in the future, having runtime compilation, access to runtime compilation is going to be a huge savings for me. It's going to mean that I can actually do programming that writes a .cl file, and then have it compile it, all while running. Like basically I can write self-writing code, is one way to think about it. And that's actually something I care about for what I do. So these kernels are compiled at runtime, and then once you've done that, you send off your work item, your kernel. It gets sort of loaded into your graphics card. You group up your work items into work groups, and the important thing there is that a single work group actually does, you're guaranteed that a single work group runs simultaneously. So if there is some amount of synchronization that you need, you can do it at the work group level. But normally you would have a big list and maybe small work groups, and your work groups all run simultaneously, but between each work group there's no guarantee of what order they're going to execute in. So that's totally asynchronous. It's done by a queuing system that you just send your instructions to. Okay? And so those get scheduled asynchronously, not by you, by the system. And what's important is, I'm skipping a whole interaction level here. That is, as a programmer, you're going to write stuff that interacts through an interface to some .lib or whatever on your system. In Linux, you're writing something that works with a shared object file, whatever. And the important thing is that shared object file, the library to which you will eventually compile against, that has to be provided by your vendor who gave you your GPU card, because that's where all the code, all the platform-specific stuff comes. Okay. And so I don't know why I was saying that, but yeah. So even the implementation of these schedulers, what actually schedules how your work groups go, that all stuff, that's done by the manufacturer, essentially. They have to provide you, essentially as a part of your drivers for your graphics card, they have to provide you these things to bind against for your code. Okay, now the thing that is still fairly complicated about OpenCL, like I was saying, is that one of the ways to get it fast, in the general model, is to have restrictions on your memory. Well, those restrictions become restrictions in an OpenCL program, and so how do you talk to your kernel? How do you talk through memory to your kernel? Well, here's your memory model. This is again taken from that same Kronos talk. I didn't contribute it, but there you go. And this is basically the idea. You have a host, and it's running somewhere down here. He has his own memory structure. However that memory is structured, that's transparent to us as programmers. There is a structure to our host memory, right? On a CPU, we have access to RAM, what we would just call RAM, but really that comes in different flavors. We really, first of all, have access to registers, and then we have access below that to level 1 cache, and then level 2, and then maybe level 3, and then all the way down to RAM. That's all transparent to us. All the interactions between those layers, when you're writing at least in C, that interaction between those different layers of memory is completely transparent. We don't have to worry about it. However, when you move to OpenCL into this larger memory structure, where your host has its own memory and then you have a compute device, all of these interactions are explicit. So there is some chunk of memory that is called global/constant memory. So this is where you would store huge arrays of data that everybody needs access to, or certain constants that everybody needs access to. Then within an individual work group, all members of a work group have access to a local memory, and then each work item has access to its own private memory. And if you want to transfer something from one of those types of memory to the other, you have to do it as a programmer. You will have a buffer that's allocated specifically in one of those locations, and you will have to copy the data over to the other location. This is not something that, these types of memory though do have a speed increase or decrease to use them, just like your caches in a host memory, or they may not. Again, this is actually comes down to the fact that it's device dependent. So the idea is that you have access to all these different things. Maybe they're really all just one big chunk of memory that is all the same speed to access, but you do have to make the transitions between them explicit. So in your code, there will be times when you're literally just copying memory from one place to another so that something else has access to it. And those places where you have to do that, that's where your slowdowns come in. The fewer times you have to transfer data between just memory, and the less time you waste not computing something, the faster your code will be. I think I didn't mix that up, but I might have. The less times you have to do that, the faster you'll be. Okay? So that's one of the things that there's a lot that goes into optimizing good GPU code. Namely, you're going to need to think a lot about the memory structure. You're going to think about how your work items parallelize with each other, that sort of stuff. Okay? That's the memory structure of OpenCL. So what does an OpenCL program look like? Here's the basic structure of an OpenCL program. You'll actually see specific code in a bit for my example. Namely, one of the first things that you'll do is you're going to create what's called a context. A context is really just some data structure that OpenCL defines for us that keeps track of everything. It somehow is going to know about all the devices in your computer. It's going to have your actual command queue, so this thing that you're going to send, like, okay, I want you to start running this kernel now. You tell it how to run it, sort of, but it then decides, okay, you told me to run this kernel, I'm going to schedule this here, this here, this here. There's some command queue that keeps track of that, all these sorts of things, okay? So you will create a context. You'll be able to get your devices at this point that you can actually work on. You can create your command queue directly from your context. Then you get to start doing some fun stuff. Then you have to allocate your buffers. So this is the idea. You're going to have to say, I want a big buffer of memory stored in the global space on my device, and it should be this large. I haven't told you what to put there yet, but that's what I want. I want this buffer. Just give me this memory that's over there on my GPU card. You can then, at this point, basically load and compile your kernel. Again, this is all done at runtime. Now you can copy data from your host memory into your device memory. You can tell it once your data is over there and your kernel's compiled, everything's been set up, you can execute your kernel. But the problem is, once it executes all the data, every computation it does is still in its own memory. So then you have to transfer your results back from device memory back into host memory so you can analyze your data, do your next time step, do whatever it is that you're doing in your code. Okay? So this is the basic structure of an OpenCL program. Are there any questions before I do like 4 or 5 pages of code so that you see what all these would look like? I'm going to go quickly over it because it's not necessarily, I'll point out what's instructive. So this is the example we're going to do. We're going to do vector addition. Completely parallelizable operation. I have a million things in one vector A, a million things in another vector B. I want to add them together and get a new vector C. That's what I want to do. Imagine that's what I want to do. Every single one of those computations is completely independent of every other. This is a perfectly parallelizable example. Okay? And so that's what we're going to do. On a CPU, this would look like a for loop, going from 1 up to n, adding AI and BI and storing it to CI. What does it look like on a GPU? Well, on a GPU, you have to decide what your smallest work item is. The smallest work item is to add a single element to another element and store it in C, and you just have to know which element you're working on. So at some point, you're going to have a piece of code that does something like, which guy am I? Who am I? Who am I working on? I'll get my global ID to do that. And then once I know who I am, I'll do my computation, and that's it. My kernel, my whole lifespan is to figure out who I am, do my computation, and be done. Somebody else can now use that portion of the GPU to do his part of the work. Okay? This is an example. The code I'm going to show I also stole. I'm really good at stealing stuff, but I do try to attribute who I steal the stuff from. A fellow Eric Schmistad, I have no idea if that's how one pronounces his name. He has an interesting blog where he was from about a year ago, where he started looking at OpenCL, and he did vector addition as his first example. NVIDIA has tons and tons of code samples on their website that you can go and use as well. I have a little trouble getting one of their things to compile, and that's why I said, screw it, I'm going to use it in something simpler. But NVIDIA has tons of code samples. There's code samples all over the place for how to use OpenCL or CUDA or whatever you are interested in doing. Let me also caveat everything here with, I've been interested in GPU computing for quite a while. It became sort of fairly popular in the scientific computing community. You know, maybe even 2 years ago I started hearing a fair amount of people going, oh, how can we do this on a GPU computer, that sort of stuff. And then another year ago I went to a conference in Reno, and there's entire sessions on using GPU computing. And so I've been academically interested in GPU computing for well over a year. The first GPU code I wrote was last night at 5 p.m., and it was this one. So there you go. So just so you know, full disclosure here. So what does the example look like? Here's your kernel. So this is stored in a file. I just called the file vectoraddkernel.cl. So it's the kernel for the vector add operation. It has to be stored in a .cl file, and it looks a lot like C. It looks like, you know, I've got a function called vector add that takes in a pointer to an int, another pointer to an int, another pointer to an int. Those are my arrays A, B, and C. I have to get my ID, and I do my single operation, and I'm done. And you just notice a couple things floating around that sort of make things not quite C. So there's this underscore underscore kernel at the front of the function. And then there's global at the front of int A, int B, and int C. And these are all just directives telling the OpenCL compiler, the thing that will happen at runtime, where it should be looking for A, B, and C so it knows how to compile this kernel. It should be looking for them in global device memory, and that this function is a kernel function. Okay? So this is all that a kernel looks like. You write this, it's stored in one file on its own, and then you go and write your C program. So what does your C program look like? Well, this is where things get a little more complicated, because as you saw in the model, there was a lot to do. Get your context, get your device, get to this, get that, and then finally the run. So I'll point out all these different things along the way. There's, like any one of these open systems, there's tons and tons of variables you have to keep track of that tell you something in the long run. The one here that's really important is that I'm getting my devices here. So at some point, I pass, where is it here? I have a CL device ID called device ID. And at some point, I pass in that guy to get device IDs, and he returns one back. He actually could return multiples if I had multiples, but I didn't, so it didn't matter. Code runs like this. I get my devices that way. What's actually important about this? Is that therefore extends. It could be that maybe you have multiple devices on your computer that OpenCL recognizes as possible things to run on. And you get to pick for your application the best one. You can, once you have this device ID, you can start querying it for what it's capable of. So I haven't mentioned this yet, but one of the things that they do on a GPU to make sure that it's really, really fast for graphics applications is they make it so that they only do single precision floating point arithmetic. Whereas in the scientific computing community, we would love to have double precision floating point arithmetic because we want that accuracy. We want stuff on the order of 10 to the negative 16 instead of on the order of 10 to the negative 8. We want this accuracy in our floating point numbers. And they restrict that. You can spend extra for GPUs that actually do have double precision, but then we don't get to use the gaming ones, which are at least relatively cheap. I'm talking like, the difference here is like you can spend $2 grand on a graphics card that has double precision floating point, or you can spend $400 on one that has single precision, and then just try to fix that later. Handle the fact that you just did your computation in single precision later. You're probably better off money-wise doing that. Okay, so you can get all your devices, you can query them, whatever, you can pick one. I just pick whichever one it sends back to me, because I only had one. You can get your context, you can get your command queue. These were all just commands to do the things that I was talking about that you would have to do at some point in your code. This is where things get interesting. You have to tell it, I have buffers for A, B, and C. I have A, B, and C in host memory. These would have been defined at the top of my routine as arrays of some length that you probably allocated dynamically. But you also then have to say, okay, on my device, give me a memory object that I'm going to call A here, a memobj, and it's in that context, it has this size, whatever, so on and so forth. Give me these buffers as well. Then you can, once you've allocated those buffers, you can actually copy your local A and B into those buffers. So here, capital A and capital B are host memory structures, whereas vmemobj and amemobj are things that are on my device. I've copied it, all my data is set up, I can compile my program. So this is the idea about runtime compilation. I build my program that was stored in, you can't tell here, but program was actually a string. What happened earlier in the code, I read from the file into a single string, and then I send that string off to create kernel. I have my kernel, then I have to somehow link up those memory structures that I defined. You have to link up amem, vmem, and cmem with arguments 0, 1, and 2 of my kernel. So now I've linked them up. And then I can finally actually execute it. And this is where all the magic seems to happen. A single command does a full loop. I've broken it up into work groups of size 64. The entire list has to get done though, so there's a global size, a local size. You run, and this thing finishes at some point, and it has at that point filled your cmemobj with the results, but you have to copy that back into your host storage here. So you enqueue a read instead of a write, and you have C. And how does that program run? So I ran this on my home desktop, which is running Fedora 17, Linux Fedora 17. It has an Intel i7-3770, not overclocked or anything. I don't want to water cool anything, I'm lazy. So it's a quad core with hyperthreading. Not that I get to take advantage of that in my host program. My host program is just serial. It's not running multiple threads or anything. And the card that I was running it on, like I said, was an NVIDIA GeForce GTX 570, which has 480 CUDA cores. Just to give you an idea, the 570 is maybe about 1.5 years old. NVIDIA recently blew AMD out of the water in terms of capabilities. They released their 680 and then their 690, which is basically two 680s on the same board. And they have, I want to say, around 1,200 CUDA cores. So they're definitely a lot more powerful than your my 570. I would love to spend a little bit of money to get some 680s just to see how many more frames I get in my games. But we'll see. Or no, actually it's for my computing, right? That's the great thing about this. I can use state funds that way, I think, maybe. I don't know. Anyways, so what are the results? Well, if I ran that program and I ran it over a sequence of array sizes, that's what I've done here. Again, I wrote this last night for the first time ever and ran it. And if I run that over a sequence of array sizes, and I tell you two numbers, I tell you the speed ups, either with and without overhead. So I'll tell you what I mean by the overhead in a second. You see a pretty good graph that is linearly increases. This is on a log-log scale, so a linear plot here is linear in general. There's a little, they're wavy, but that's, I'm not going to be able to explain that. I don't know why. I know the basics of why these would be, randomly hitting proper lengths of your cache line, all these, there's pretty complicated stuff that one could do to optimize your code, and I haven't done any of that here, so whatever. But what's important is speed up 10 to the 0. You see the 10 to the 0 somewhere in the middle? That's speed up of 1. That is to say, anytime you're above 10 to the 0, you are doing better on your GPU than you were on your CPU. So what am I comparing to? I'm comparing to a single for loop, is what I've done. And you see that with no overhead, that happens pretty quickly. And it gets pretty high. I get speed ups on the order of 10 to the 4 eventually. This is a linear growth here. I'm getting near perfect parallelizability. That's what we hope to get. Now, in the interest of maybe being fair, add the overhead in. What's the overhead? The overhead is compiling your kernel, sending your data over, sending it back, and then checking the time of that. Even still, with overhead, I do eventually break even. Happens somewhere around list size between 10 to the 8 and 10 to the 9. And so, at some point, you do break even. Now, you might think, well, that's the only line that matters, is the one with overhead. It's not quite true, because the goal of a good program would be to amortize that overhead. You would want to load your data once, do more computations on it, do more iterations of your time-stepping scheme, do something before you then have to pull it off. Or, even better, you only have to compile your kernel once, even if you're going to use it multiple times. So that overhead goes away. So a lot of the overhead can go away. You can amortize it over a longer running program. This being, again, a simple program, it didn't really matter. But even still, you see that you can get speed ups even with the overhead. So this is why GPU computing, and that's pretty much it for me. There's the 3 references that I used to come up with a lot of this. Kronos is the guys with the standard. There's this interesting talk from UIUC. They had a summer program about it. And then that guy's blog where I found his code. There you go. Thank you. I apologize for going over. Any quick questions? Do we have time for quick questions? Any quick? Okay.
All right.
You can always talk to me later.
Thanks, guys, and we'll see you next week.